Yo, physics nerds, what's up? Time to do a review of the topic of gravity in the unit dynamics. Okay, let's get going. So, first things first, couple pointers about gravity. Gravity is the mutual force of attraction between massive objects. Don't forget, mutual means both parties. So, like a mutual agreement means that both people agree. So, the reason why gravity is called a mutual force is if one object attracts another object gravitationally, then the other object attracts the other one gravitationally. So, both objects feel the same force. The other thing is that gravity is always an attractive force. It never repels. Magnets and electricity, so the force of electromagnetism, can be attractive or repulsive. Gravity only attracts objects with mass. Another thing is that gravity is the weakest force in nature by far that we know of. It is billions, or you could just say trillions of times weaker than electromagnetism. Um, Gravity varies directly with the mass of the object. So more mass, more gravity. Okay. However, the force of gravity, similar to other things in nature, such as the strength of an electromagnetic field, or how bright a light is, or how loud a sound is, there is a spreading out of the force. So it gets weaker and weaker with distance. So the force of gravity, like those other things I mentioned, is inversely proportional to the square of the distance between the centers of the objects. Okay, that's why it's called the inverse square law. So you're going to divide the force of gravity by the distance between the center of objects squared. This means that if there's a little bit more distance, the gravitational force gets much weaker. And if you bring objects closer together and there's less distance, gravity gets much stronger. Okay, here's an example, right? If you have a 1 meter in area, I guess, piece of paper that you're holding up, and you have a flashlight 1 meter away, you would say the quantity of light is 1, and you would divide it by 1 squared. 1 squared is 1, so you get that brightness, meaning 100% of the brightness. And by the way, even though it's brightness of light, gravity works the same way. And so do electromagnetic fields. So let's say you double your distance from the light source, or again, we could just think of a gravitational field source, like a planet or a moon. If you double your distance, you actually end up getting an area where the force gets spread over that is not just twice the original area, it's double the distance. So you square that. So 2 squared is 4. So this is 4 square meters, which means that the brightness of light, or the gravitational strength, gets divided by 4. So you have a quarter of the original strength. Same goes for 3 meters. So 3 meters farther away, that's 3 squared, that's 1/9. So that's 9 times weaker of a force that you would feel. Okay, so this is called the inverse square law, and as you can see, it applies to a few fields in nature. Here's a graph of the force of gravity versus distance. Okay, so if you start, let's say, at the surface of Earth, you are 1 radius. In this graph, they're using d for distance, but you would typically see r for radius because you're 1 radius from the center of Earth, right? So at 1 Earth radius, you would feel 100% of Earth's gravity, let's say. But at double the distance, that would be 2 squared. So 2 squared is 4, so you would feel 4 times less gravity if you doubled your distance from Earth's surface. And 3 times the distance from Earth's surface, that's 3 squared, that's 9 times weaker gravity, and so on and so forth. Okay? So if you have a graph of gravitational force versus distance between the center of objects, you should see an exponentially decreasing graph. That also explains why, when we get to this equation later, which is the Newtonian universal gravitational equation, you'll notice that you divide by the radius between the objects squared. Okay, here's another example. If you're at 1 radius from the Earth's center, which is all of us standing on Earth's surface, you feel normal gravity. If you double your distance from the Earth's surface, you feel 4 times less gravity. If you triple, 9 times less gravity. If you quadruple your distance from the surface of Earth, you feel 4 squared is 16 times less gravity. Interesting thing, at the center of Earth, gravity is actually 0 because instead of getting pulled down, all the mass is around you. So technically, there's 0 gravity at the center of Earth. Interesting. Okay, we did these check-ins in class. Let's keep it going. So interesting thing about gravity. Gravity is actually not just a force field. It's actually a bend in space. So it was hypothesized by Albert Einstein using some math, or a lot of math, I should say, that gravity was actually caused by a bend in space-time. And there was actually an experiment done in May 29th of 1919 during a solar eclipse where the moon blocks the sun's light, conducted by Arthur Eddington and Frank Watson Dyson. And what they were trying to do is see if any stars that shouldn't be visible because the sun would block them would be visible because their light got bent by the sun's gravity around the sun. And they would be able to test this by waiting for the sun to be covered up by the moon during a solar eclipse. And it turns out that actually, yes, there were some stars visible at the edge of the sun where their light, if it was going just in a straight line, should have been blocked by the sun. But because of the sun's gravity, space actually gets bent and light travels through space. Therefore, the light got bent around the sun and it actually made the stars visible. So we actually know this is true. Gravity is actually a bending of space, and time is part of space, so we call it space-time. So you could think about this as you sitting on a couch or a bed, right? You bend, your mass bends the bed. You make a dent in it. So now picture if the bed or the couch you're sitting on is invisible, so you can't see it, right? Like space is just invisible. But now let's say I put a marble next to you on the couch or the bed. The marble comes towards you. So if the bed or the couch was invisible, you'd be like, oh, I'm attracting stuff towards me. But really what's happening is you're causing a bend and the marble's rolling into the bend. And it turns out that's actually what gravity really is, as far as we can tell from all experiments. So what we feel as gravity, as just a pull, it's not so much a pull, it's that you're trying to walk in a straight line, right? So think about a hill. If you're trying to walk in a straight line and you keep walking in a straight line, if there's a dip, let's say down into the road, when you walk forward, you have no choice but to follow the dip downward. And for a hill, if you're walking in a straight line, again, you have no choice, but you're walking in a straight line, but you end up going up because there's a hill. So again, gravity is caused by objects with mass, including your body, warping space. So any object with mass warps space around it, or space-time, which means anything with a mass creates a gravitational field. Yes, even you, and especially, apparently Socks needs to go to the gym and stop eating so much. All right, and we have evidence of this. It's super cool. We see when we look out into space with telescopes, we could see that the light from stuff in space gets bent by objects in front of it on the way to Earth. So again, here's a galaxy, and the light's coming out of the stars from the galaxy. But if there's a really big, heavy galaxy with a lot of mass in front of our view from Earth, what happens is the light is trying to go in a straight line, but it ends up getting bent around. And we end up seeing weird images where things get doubled up. Okay, it's called gravitational lensing because it's almost like me, my blind butt, looking through my glasses. The lenses of my glasses, whether they're made of glass or plastic, the light gets bent as it goes through them. So gravity bends space, and therefore it bends light. Super cool. All right. And of course, in our class in physics, we've been studying gravity around Earth. It's not totally constant. As a matter of fact, where there's more rock and mountains, there's stronger gravity on Earth. And where there's less rock and mountains, gravity is actually a little bit weaker. So we actually have gravity maps of the Earth where it shows where gravity actually is a little bit different around Earth. Slight differences, though. This image is exaggerating the differences. Okay, speaking of gravitational fields, here's another thing. Gravitational field strength is an equation on the reference tables. We'll get to it in a moment. And the equation given on the reference tables is G equals Fg over m, which stands for gravitational field strength is weight, which is Fg, force from gravity is weight, divided by mass. And by the way, if you look at the way the units work out, we know that force is measured in newtons, and it gets divided by mass, which is kilograms. However, if we recall from earlier studies, we know that a Newton is actually a kilogram times a meter over seconds squared. So if we have a kilogram times a meter over seconds squared, and we divide that by a kilogram, kilograms cancels out, and we end up with the units meters per second squared. And we've seen that before. meters per second squared is acceleration. So gravitational field strength is the same exact thing as acceleration. So and Albert Einstein, of course, actually pointed this out many years ago, that there is literally no difference between gravity and acceleration. So gravity is an acceleration. So now, because gravity is a attractive force only, gravitational field lines on a diagram will only point inwards towards an object with mass. All right, so yeah, if you see any gravitational field lines drawn anything other than pointing inwards, that is incorrect. Okay. And by the way, so that equation, gravitational field strength is weight divided by mass. It was found by measuring the weight of objects and their mass. And if you plot that on a graph, you end up getting a straight line where the slope, well, if you look, right, don't forget slope is y-axis divided by x-axis. So if you see the y-axis is weight in newtons, which is Fg, and the x-axis is mass in kilograms. So that means if you find the slope, you're getting weight divided by kilograms. Well, we said in the equation, weight divided by mass in kilograms gives you gravitational field strength. Therefore, anytime you have a weight versus mass graph, if you find the slope, what you just found was the gravitational field strength. So in this example, we can find the slope by doing 24 minus 0, so right, change in y, divided by change in x, which would be 15 minus 0, if we choose to find the slope there. 24 divided by 15 gives us 1.6. Therefore, the gravitational field strength is 1.6 newtons per kilogram, which is the same thing as 1.6 meters per second squared. And we know this is not Earth because on Earth, it would be 9.8 meters per second, right? 9.81 meters per second squared. This is actually the gravitational field strength on the moon. All right, so on to the last part of this topic, which is using the universal gravitational equation. So let's take a look at that equation on the physics reference tables. So if we go to the back page here on mechanics, or also known as dynamics, let's see, there are the two equations here that have to do with this topic. So right here, we have gravitational field strength is weight divided by mass. But right here, we've got this long equation, which is force of gravity, which is the same thing as weight, is capital G, which we see here says universal gravitational constant. M is mass. So as you can see, it says mass 1 and mass 2. So we're going to multiply those three numbers. And then it says R, which is radius. What do they have it as here? Radius or distance between centers. Okay. So, sorry, lost track of it. Here. Okay, so this is the equation. So I'm going to rewrite it in a moment. And so let's try, if you were in class, we did this, but I'll run through it one more time. So here's a question. All right, and this is my favorite planet, Neptune, and there's its moon, Triton. So we're going to practice using the universal law of gravitation equation. The question says, calculate the gravitational attraction between planet Neptune and its moon, Triton. And now some information given to us is that the mass of planet Neptune is 1.02 times 10 to the 26th kilograms, while the mass of its moon Triton is 2.14 times 10 to the 22nd kilograms. And we are also told that Triton orbits planet Neptune at an average distance of about 3.55 times 10 to the 8th meters. Okay, so I'm going to keep that information right there, and I'm going to start working the problem out over here. So first things first, remember step 1 or A, whatever you want, is to write down what information is given to us. Okay. So to make this easier, I might do, let's see, my two screens. There we go. All right, and then you can go over there. All right, so let's see. I'll write down that the mass 1, I guess I'll put down as Neptune's mass, which is 1.02 times 10 to the 26th kilograms. Mass 2 is Triton's mass, 2.14 times 10 to the 22nd kilograms. The radius, which is the distance between the center of these two objects, is 3.55 times 10 to the 8th meters. And there's one other thing given to us, which we need, is the gravitational constant, universal gravitational constant, capital G, which is 6.67 times 10 to the negative 11th newtons of force times meters of distance squared divided by kilograms of mass squared. And yes, we actually do want to write all that down, because if you show that you know these values and their units, you actually get credit. You get a point for that. Okay, so newtons times meters squared divided by kilograms squared. Okay, so that's step one. Oops. Can I zoom out a tiny bit? No? All right. So there's step one. There's our given information. So try to do this along with me. So there's the given information. Step two, you always want to remember, is the equation. So I'm going to write the equation from the reference tables. Force of gravity is the gravitational constant times mass 1 times mass 2 divided by the distance between the objects squared. All right. And third step is substitute, meaning let's plug everything in. So here we go. Force of gravity equals, now here's the thing. If you put the units here, you don't have to plug them in to the equation, and you already get a point, okay? So I'm going to plug in the numbers only, the values, or the magnitude. 6.67 times 10 to the negative 11th. I already have the units up there. Mass 1 is 1.02 times 10 to the 26th. Mass 2 is 2.14 times 10 to the 22nd. And then I have to remember to plug in to the bottom of the equation the radius, which is the distance between the object's centers. But I have to remember to tell people to square it. So believe it or not, by doing that, this is already 2 points. Okay? So you get a point for showing the given information with units, and you get another point for showing your equation and substituting in properly. So this is 2 points right here. You actually do not even need to solve this. Okay? So you're getting credit for showing the information and the equation with everything substituted in correctly. For the heck of it, I'll solve it to wrap this up, but you don't even need to for full credit. This would be an extra point. So I guess I'll give it a shot. I don't know, though. It looks like my apps are crashing on me. Maybe the Chromebook's overheated or something. So then you know what? I'm just going to leave that off, because you already, again, this is full credit. You get 2 points on a 2-point question. If you were to solve this in a calculator, that would be a bonus point. Okay? Just be careful about following the equation and make sure that you divide by the distance between them and you square it. And make sure to show all the units there. It's the hardest part of this topic. All right. I hope this helped. Good luck.